Howdy, folks. Howdy. Good afternoon. Welcome to Physics 5B. Very happy to have all of you over here. I see several familiar faces. I may have forgotten many of the names, so please don't mind if I'm not able to recall your name, but I do recall the face. Before I start, for how many of you it is your first time here in this classroom? Wow, it's a lot. I'll tell you a story. Yes?
Wait, do you mean like this particular?
Yeah, this particular room. Yeah. I'll tell you a story. There was a patient on the operating table, very nervous, very, very nervous. And they said, "Doctor, I'm really scared and nervous." I said, "Why?" "Because it is my first time." The doctor said, "Don't worry, I got you. It is my first time too." So, it is my first time too. We will have to find a way to get this work. I don't know if you like this or you hate this. I think I'm already hating it. For those of you who have taken a class with me, I think you know why I'm already hating it. Those of you who haven't, the story goes that I don't use slides at all. Well, maybe sometimes, but generally I write on the board. And I like to keep things written on the board, and I slide the boards up and down so that things are there and I can draw connections. We also have a lot of students who who either due to disability or for any other reason need some more time to process the information. So I don't like to erase them, nor do I like to use slides, because when I use slides, there is a material in there, it's gone, there's a new material, it feels too rushed. So I like to write on the board and then leave it up there for a while. But here, I'm already seeing some challenges which we will have to adapt to. One of the challenges, there is nothing to slide up and down. I trust that they record. I don't know why they have this stupid, long, gigantic screen from there. Like, what are we here to watch? Like a IMAX show or something? Walking into the classroom, that's how I felt. Like, I'm a showman. Here, there's a stage built in for me here to make a performance. That's not my style. I am not here to engage in any performance in here. But a few things that we will have to adapt. Since I'm going to be writing on the board, my writing is not always going to be this dark. It would depend on how bright the markers are. It may not always be this big. As I write in a flow, it can become smaller. Therefore, all of you guys should move toward the front of the classroom. You're not going to be able to spot what I'm writing. So there is plenty of seats up here. This classroom has a space of like 600. We are about 300 or 310 in the class. So come forward. If you're sitting in that back side over there, the second half, no more than the first 3 rows. The writing will begin to look very small, and if you're not used to coming up in front, it will be harder for you to come up front once the class gets going. So during the exam, we will span out. We will use the full space to spread out, but now start coming forward so that you can begin to see how big it is. Now, if your eyesight is outstanding and you can really read all of this stuff, in fact, smaller than that, more like my writing can become like this. Sit as far as you can so that you can read this very clearly. The goal is not just to read this, but read equations. Equations will have a suffix, like it will be something like, you should be able to read this, what the suffix is exactly, okay? So stay up close. I can already see that this thing is blocking your view, so I will make sure that I write in this zone over here. In case I forget, please just remind me, all right? So that way we will not encounter any bottlenecks due to this thing over here. Sounds good? Okay. So with that, let me get started with a few things. First of all, let me tell you why do I like teaching this class so much. The Physics B series. Well, I like teaching the Physics C series as well. But the B series is an absolutely fantastic class. You know why? Because it is literally a continuation of everything you learned in Physics 5A, with very few exceptions. But of course, it is not just a continuation, it is application of what you learned in Physics 5A. So here we will really take concepts we went over in 5A and take different examples, like for example fluids. You haven't seen fluids in 5A, of course, but what we will learn is how the concepts in 5A are used to solve problems related to fluid dynamics. What is buoyancy? What is Archimedes' principle? What is Bernoulli's equation? These are all jargon. Knowing jargon is the most pointless thing. It is about what do you do with it? How will you use it to make calculations? And you will see that the way you learned, the skills you learned in Physics 5A, the method of solving problems that you learned in Physics 5A is going to be applied in here, not just the method, the principles as well. You will use net force equals mass times acceleration. You will use work. You will use the concept of power, the concept of energy. All of these things are going to be used when we study, say, fluids. The same thing will apply when we study oscillations. Now, of course, there will be a few other things that we will also see, how different concepts in oscillation and some new terminology and new concepts, but the broad process of problem solving is going to be very similar. This is very different from the Physics C series, where we do electricity and magnetism, where we do use concepts from Physics 5A quite a bit, but we have very different types of interactions. The interactions there are electric and magnetic interactions. We no longer have like tension and friction, etc. in the C series when we do electricity and magnetism, but we will have similar concepts here that will apply when we do Physics 5B. And therefore, in Physics 5B, you learn a lot about nature, a lot of applications pertaining to not just engineering and physics, but even about the human body, physical processes in our body. Okay? And therefore, this is a very, very fun class to be in. At the same time, since it is a build-off of Physics 5A, and it is application oriented, you can clearly see that the concepts between themselves may not be related. They will all relate to 5A, but between themselves there will be no relationship. The things that you learn about fluids may not directly apply to things in oscillation. Is that making sense? The things that you learn about springs and oscillation may not directly connect with optics. In fact, optics is the only thing that has no connection with Physics 5A. Generally, optics is put into like the 5C group if the courses are taught in a semester system. But we have a quarter system, so we have to slice that up and put things together. And optics fits in well, actually, in Physics 5B, because we talk about interference and diffraction in addition to geometric optics. Geometric optics is about lenses, mirrors, telescopes, microscopes, and then interference and diffraction is completely another phenomena, but that interference, diffraction, etc. relate to wave motion, which is an important part and a critical part of Physics 5B. And so putting in optics was a good a thing to do in here, because we can do both wave optics and geometrical optics in the same course than doing one type of optics in one course, another type of optics in another course. So, so that's the nice part of this course. The hard and a good part of that as well from your perspective is if you fall behind on one component, your learning is not immediately impacted in the other component. Say you don't understand anything about optics, your understanding of fluids is not impacted because fluids is a completely different topic, not connected, which is not the case in 5A or in 5C. The concepts are sequential, you don't understand one, you're directly impacted in the next one. So that's one good thing. The difficult part is since it is a whole bunch of different topics, different applications, it is going to be fast-paced. And you have to keep up with the class. You have to be very organized and disciplined and learn on time. Okay? This will be important, otherwise it will just feel like, oh my God, I have so many things to learn, I have so many things to catch up on, and it will not make sense to you. You will feel like, what is the connection between them? There is no connection between them. The connection is with 5A, largely. Sounds good? Now, the second thing, an extremely important thing, there is a lab component for this course which is a required class. However, the lab is treated as a completely independent course. It is also designed to be largely independent of the lectures. The purpose of the lab and the lectures is to give you two types of exposures. One is the rigorous principles we learn in class and how to apply them in problem solving. The goal of the labs is to give you this experiential sense of learning. You experience by doing and try to understand what concepts may be related. You are not expected to be an expert knowing all the principles as you enter the lab, but you are expected to go prepared before you go for the lab. Now, in a class like this, it is very difficult to nearly impossible to make sure that the lecture is always delivered before the lab. It is not going to happen. There are going to be some labs where you will see the content in class before you go to lab. For example, today I will start with fluids. You're not going to do the fluids lab now. You're going to do the fluids lab in a few weeks from now, and you will be really well, you will really know, okay, what's going on in this lab. But starting this week, I think your labs are starting this week, right? Yeah. So starting this week, your labs are on optics. I'm not going to cover optics in class. But what will happen is you will learn about optics in lab, you will get this experiential learning exposure in lab, get a sense of some of the concepts, and then when you come to the optics lecture later in the course, you will be able to draw that connection because you have done it hands-on. Is that making sense? But for this, in order to be successful with this, you must absolutely read the lab manual thoroughly. It has been written keeping this in mind. It is not written to make you an expert about the topic, but it is written in a way to give you enough exposure about a concept so that you can do the experiment and understand the terminology. What is a sign convention? What is a convex mirror? What is a concave mirror? What is a virtual image? These concepts are in there. You need to go through this very carefully and go prepared to lab. This is going to be extremely important. Now, the lab schedule has already been published or will get published in Canvas. So you will know ahead of time when you have what lab. Start preparing for the lab a week or two before the lab. Of course, not the first week, but make sure as soon as you go home today, get the lab manual from Canvas, start reading the first experiment, get yourself familiarized with it. For upcoming labs, start reading them a week before at least the lab starts so that you have enough time to process the information. Your goal in these labs is to get yourself the hands-on learning experience, to play with things, to see the challenges of doing experiments and understanding, okay, this is what a focal length is, that is what a real image is, this is what a virtual image is. You get that, you come to class later, you will understand it better. And in some cases, like I said, I will be teaching the concept first, you will encounter in the lab later. Sounds good? Okay? All right. Now, the broad structure of the class, we will have a few components. All of these components up to number 5 are required and mandatory. 6, 7 are optional. I'll talk about them one by one. Number 1 is showing up for class, attending lectures. And in here, I have a lot to share with you. First of all, when you come to class, you should come with a method for taking good systematic notes. Like I said, I don't use PowerPoints. I write on the board. This is going to get recorded, but look where that camera is. Look at this distance. I have no guarantee, and they are going to record the full show from left side to right side. I have no idea how big this is going to look in the recording. So, come over here and make your learning efficient. Additionally, I hate watching videos on computer screens. It's stressful. So, come over here, take good notes, and ask questions in class. This is one of the most important things in my class. I really like it when students ask me questions. I like getting interrupted. Interrupt me. You don't understand something, just raise your hand and ask the question. It is perfectly normal to zone out during a lecture. It is abnormal if you don't zone out. If you do zone out, you come back, just raise your hand and ask a question, I will clarify it. I will not tell you I explained it. Unless it is a lot of material I explained and you zoned out for quite a bit of time, then that may not be possible. But, which is all the more reason why you should be taking notes. When you take notes, the probability of zoning out is significantly reduced. Secondly, there is something that sets humans apart from all the animals. Number 1 is the fact that we could stand up. There's no other animal that can walk on 2 feet. And doing this freed up the hands. And that is how we changed the planet. That is how we have manipulated nature. No other species on this planet has succeeded in manipulating nature. But in order to do this, 2 things have happened. One is, it required enormous amount of brain space. That is why it takes 9 months for a human baby to be born. 9 months for this development. But this development has saved a lot of space to document what we are doing with our hands. Locomotion and what we are learning with our hands. That means what you do with your hands registers way, way better up here, gets embossed. It's in the genetic code to get embossed in here, and retention is significantly enhanced. That's why we use the term learning things hands-on. We say go have a hands-on learning experience. What does that actually mean? You learn by doing something. You learn when you write. So never learn from any class by trying to watch a video or a performance. Instead, if you actually want to learn, be it here in the classroom or be it in a team meeting wherever you are working, keep a notebook and write. The stuff that you write, you will remember. The stuff you don't write, you are at risk of forgetting. Okay? So what I would like you all to do is make your learning efficient and structured. By structured, I mean keep a place for documenting your lecture notes. Yes? Sorry? That's a very good question. What do you do if you have to miss a lecture and the recording is not as good? First of all, try your best not to miss a lecture. Second, that can happen. You may miss a lecture or 2. Form partnerships in this class. I am going to talk about this very, very soon in point number 2 in here. This is going to be important in many ways. We will come to that. And when you form these partnerships, get notes from the person who attended class. Sounds good? Okay, now what I want you to do is, if you are using tablets, even there, make sure you have a folder that is organized. If you are not using tablets, you are using books like I do, good. Bring the books, but make sure this book is dedicated for Physics 5B. If it is a thick book, at least the first half is 5B. Don't mix up chemistry and mathematics and everything in there. Do not even mix up practice problems from this class in the notebook. You are taking lecture notes. Because lecture notes are concepts and strategies and ways to think that you want in one place that is easy for you to find out. You are taking many other classes. Come exam time, you will need a quick reference to fall back on and find out what you want very quickly. If you have mathematics and chemistry and statistics and physics all in one place, or even physics problems, homework problems in the lecture notes, you will not be able to find the information when you want it. So make your learning efficient. Second, this is priceless tip. Bring colored pens to class. There are going to be, in science, successful science is done through careful attention to detail. And science operates on definitions. Definitions are very sensitive, very, very sensitive to the terminology used in there. You change one word in a problem, and the approach to solving it can change dramatically. In class, I am very careful about highlighting these, and I will point out, I will mark, underline, or ask you to put it in a box or make a red colored mark. I don't have red colored pens. I may say mark this with a red box or something. You should mark it. It will make your learning that much more efficient. Okay? So, structured, organized, good note taking is going to be very important for you to create your notes from lecture. The second thing that we will do, that you should do, and is a required learning component of the class, is coming prepared for lecture. This is going to be a very important exercise in my class, something you are not used to doing, I know, or at least those of you who haven't taken a class with me are not used to doing it. Often instructors give reading assignments, right? And they say read this chapter or this section before you come to class. I don't do that. What I want my students to do is, after a lecture, I want them to rework the exercises I did in my class. Because watching doesn't lead to learning. You learn when you work out the problem. So the exercise that I want you to do is to take the example I will be doing in class and rework it before you come for the next lecture, not within the next 3 lectures. Next 3 lectures is if it is an emergency, you have a midterm for a class and you don't have time, that's a different thing. But generally, every week, before you come for a lecture, rework the problem done in the previous lecture. And the reason for it is, perhaps you could guess, the class is going to be very fast-paced. Topics are just going to move from one topic to another topic, and if you are not up to speed, you will not follow what I am talking in the next lecture, or you will only follow in a very skeletal manner, but not quite grasp it. Your learning will be significantly inefficient if you try to learn that way. So, one of the things that you should do is, after you go home, say today's lecture examples, before you come for Wednesday's lecture, rework those examples or exercises or derivations, whatever they are. Thereafter, you would be going to collaborative discussion sessions. Now, there are many, many reasons for me doing these active learning collaborative discussion sessions. One of the big reasons is the demand of today's times. Nobody works today in isolation. No employer walks a brilliant engineer or a scientist who cannot work in a group, who is so good that other people can't work with them. We all work in teams. I work with a team, you will work with a team. And in a team, you are not going to find people who are as good as you. There are going to be people who are more efficient, some who are less efficient, some who are more talented, some that are less talented. We cannot just fire people from the team that way. The goal is to bring everyone together. If you are really talented and you are on top of the material, your job is to help your team grow by being the mentor in there, by asking questions, by helping others learn what you know. Like I am helping you learn what I know. You go in there in your small group and you help your peers learn what you know. Not tell them the answer, but help them, teach them, be the teacher. At the same time, suppose you are not up to speed, you lagged behind in a week, you are struggling, you are not knowing what to do. The idea, your perspective should not be, I am just going to give up and watch other people solve the problem. That's not a good team member either. Such team members end up stalling a project. No manager will want that. What you want to do is, if it is not expected that we all know everything. It is not possible. That is why we build teams. But the point is, the person who doesn't know should ask questions quickly and early. And you say, okay, here is this information. How am I supposed to know? What am I supposed to do? That's the big question you want to ask in your team if you don't know what to do. How am I supposed to know? What is the signature in the problem that is telling me this is what we need, this is the approach we need to take? And you want to throw that question to the group, and somebody in the group will answer this question and will help you move forward. The TAs will run these sessions, but the TAs cannot reach 25 students multiple times in 65 minutes. It is not possible. TAs will only hop from group to group and answer questions to the group. So there cannot be any individual who just is working alone and say, is this right? TA cannot answer that question. Work out, you ask the group, is this right? Let the group decide. Then the group raises a hand, you go to the TA will answer the question. Sounds good? We are here to help you, but we want to make sure that the process works efficiently. Now, in here you are going to form groups. Right here as you are sitting in class, you can form groups. It's a very good idea to form groups, small study groups, and then meet up later in the library, at a coffee shop, or wherever. We are humans. What sets us apart is that we have grown in groups and tribes. That is how civilization came forward. Use it. It is our strength. Our strength is not in learning alone. Our strength lies in learning in groups and in helping in groups. So capitalize that, form these groups, and this will help those situations where you may have missed a lecture or two. You can quickly email your group members and somebody will send you the notes from the class that you missed in case this recording doesn't come out well. I'm recording all the lectures. I will release them to the entire class, but again, I don't know what is being recorded and how good it is. The other element in the course is problem sets, which I will, sorry, I should not have written ETA, which I will administer through a website called the Expert TA. How many of you have never used the Expert TA? Oh, good. Most of you have. Nevertheless, I will release a very detailed announcement about Expert TA, how to register for it, how to sign up for it. It will be all self-explanatory in there. That reminds me, the Canvas shell for our course is not yet up. I'm setting things up. As soon as it is up, I will email the class and let you know. Yes?
Do discussion start this week or next week?
Discussion starts this week. Okay? All right. So that's problem sets on Expert TA. I'll talk more about it once I release it. Then we will have midterms and exams. In this context, I'm going to set up a survey on Canvas asking you for any known dates of absence. Some of you have emailed me. There is a whole bunch of people going for some auto expedition like not quite an expedition, it's like a competition, right? Yes, come see me right after class. Uh, but even though you come see me right after class, make sure you fill up the known dates of absence survey in there, just respond to it. Yes? I can't hear. Yes, labs start this week. And once again, folks, as I start lecturing, it will be hard for you. Come sit in the first block of the class or up to the first 3 or 4 rows in there. You will not be able to, I will not be able to hear you, you won't be able to read. It will be on Canvas. It's not yet up. Now, I will hold office hour sessions. I will talk about it later. And there will be several help sessions. The TAs will conduct TA office hours, and we have 2 wonderful SIs, supplemental instructors for our course. Are the SIs here? They are not here, I guess, today. All right. So we will introduce them to you on Wednesday or Friday. SI sessions, they are still trying to work out the schedule and what dates and times the sessions will be. We will make sure we have minimal conflict with each other, so times will be distributed throughout the week. Make sure you seek help early. And as far as problem sets go, these are like your homework assignments. Start as soon as they are assigned. You don't need to finish when they are assigned, but you need to start when they are assigned. The worst thing to do in this class is to try to do these problem sets the night or 2 before it is due. You're leaving yourself with virtually no time to seek help. And there is no email help. I should let you know, this quarter I have 550 students. So I get a lot of emails. If you email me, you should give me enough time to respond. And by the way, I should mention this. If you email me, you should not send me a direct message through Canvas. Email me directly here and make sure to mention Physics 5B in the subject line, not in the body of the email. Body of the email is fine. Do not email me through Canvas. Canvas does not retain email threads, and once I don't know what is happening, I don't end up replying. So email me directly at this email address and put Physics 5B in the subject line of all emails. Okay. Textbook, there is a textbook for our course. It is pretty much the same textbook that we had for Physics 5A. I will mention the textbook in the syllabus. It will be up there once I release. I'll let you know when I post the syllabus along with the dates. However, I don't follow any textbook in any particular order. So what will be important is for you to follow the order and the depth or the rigor of the concepts as I do in class. Sounds good? Okay. Now, before I start on with the first topic, are there any questions? Yes.
For organizing your lecture notes, do you recommend getting a new notebook for lecture 5 use 5A?
Getting a new notebook for 5B versus 5A is not necessary. No. The whole point here is to make sure that you are able to access you're able to find information from this course easily. So if you have a pretty thick book where first half is 5A, second half is 5B, that's not a problem. Yes. Yes, The Canvas shell for the course is not up yet, but I will, and we will, I will share all kinds of information through Canvas only. Okay? By the way, those of you who have DRC accommodations, there is one important thing to remember. You must not email me the accommodation letter. What you must do is go to the accommodate portal and place in your request for every class every quarter. Just having the approval does not get to me, and you should not email it to me. You should send it through the accommodate portal, and there is a reason why. There are multiple departments within the university that work in collaboration to make sure that accessibility is met. If you just send it to me, it doesn't go to the others. So you need to send it through the accommodate portal only. Okay? If you don't know what that is, perhaps first contact your service coordinator and they will guide you, but make sure you get that process set up. All right. Any other questions? Yes. Textbook? Yes, like I said, I will post it in the syllabus. All good? Any other questions? Yes.
Are there any quizzes?
There are exams, midterms and final. Sorry, I shouldn't say exams, midterm and final. Midterms and final, but no, there are no quizzes. The discussion work will get graded both for correctness and for collaboration, not just attendance, for collaboration. However, these are not quizzes, these are largely practice sessions where you would be practicing working on a problem. The grading on these discussion sections you will see is very light. It's nowhere close to how exams are graded, and you generally get a lot of points going to section. But you only get points if you are actually doing the work, not just attending. Yes? 2 midterms and a final.
Do you have the dates for the midterms yet?
Not yet, not yet. All right? Okay, so let's get started with the first topic in our course. So the first topic is on fluids, and the focus will be on learning the principles of analyzing dynamic, that is moving, and static fluids. Now keep in mind that the principles, while we will learn some new terminology, the approach of problem solving will be very similar to what we did in 5A. So let me ask you a question. You don't need to take any notes in here because what I'm going to do here has nothing to do with fluids per se. But let me ask you a question in here. Suppose you were to launch a projectile with some velocity at some angle, and it flies out in air and lands somewhere. You're given the angle, you're given the initial velocity of launch, the angle, and the height. These three things are given to you. And the question is, where will it land? Essentially, you have to find out d. That's the question. My question to you is, what method is most efficient to answer this question? Transfer of energy or energy conservation or kinematics? Kinematics?
Yeah, I also see kinematics.
Kinematics, okay. Kinematics. Anyone for transfer of energy? Transfer of energy? Okay, transfer of energy. Transfer of energy? Okay, transfer of energy. All right. So transfer of energy, that means you would do work net equals change in kinetic energy or energy initial equals energy final, so on and so forth. Okay. So how do you know that this is a problem about transfer of energy, or that transfer of energy can be used to answer this question?
Given two velocities.
We are given two velocities. What are the two velocities?
You have your initial velocity and the reverse condition as it is number.
So we know that initial velocity. And what other velocity? Are we given this velocity? Where? Yeah, how much is that velocity? Zero. Agree? One thing to remember, if objects land with zero velocity, the world will be a very safe place. Why? Bombs won't have any effect. This is a very important thing to remember. If objects land with zero velocity, bombs, rockets, missiles, these are all pointless things. They will all land with zero velocity. There will be no harm done. The object may land here and then roll and eventually come to rest. That's not what we are asking in here. In fact, the question did not even ask about the velocity. The key point here, the key message I want to convey here is, when you come across a problem in 5B, you have to do this exercise. You have to ask questions. What method am I going to use? Because some methods are going to be effective, some are not going to be effective. So, who can tell me when would you use energy conservation? Yes. Two different positions.
So for example, you have an initial velocity at one position, and you have a final velocity at another position. That's when you use the relationship.
So are you saying that not just two different positions, but two different, yes? When the problem is asking you to connect two speeds at 2 points, if the problem were to ask me to find out this speed here, or had given me this speed here and asked me what is this height there, if it was a problem connecting two speeds at 2 points, only then I will use energy conservation. Otherwise, energy conservation is not helpful to solve the problem. Key point here is, this question does not ask me to calculate any time. There is no, the target that I have to calculate, I need to calculate d. That's my target. Time is not my target. Kinematic equations largely depend on time. Yet, I have to see that I need to use kinematics. Why? Because I cannot use energy conservation. Is that making sense? I have to reason that out as to what approach am I going to pick given a problem. And the point here is, I think I ask my question, what are my tools? What are the methods that I know? The methods I know are kinematics. Methods I know are energy conservation. Method I know is about circular motion, centripetal acceleration, v square by r. Method I know is about momentum conservation. I see none of these apply, but kinematics can apply. And that is how I'm going to decide and choose to use kinematics to solve this problem. This question is not asking about time, but just because it is not asking about time does not lend it to the method of energy conservation. So just because time is not present in the question doesn't mean it is an energy, it can be solved with energy. Sounds good? All right. So when we do fluids, we are going to keep this in mind and recognize when to use what. Now in fluid motion, we are going to do something very, very similar as in 5A, except there is a very, very nice thing to remember as to what we do in fluids. Do you know that in order to build a swimming pool, the engineers have to know how strong the base of the pool will have to be? They have to calculate, not know, they have to calculate. You appreciate that, correct? You cannot just build a swimming pool and then just hope it will work. You need to give it enough reinforcement. You need to make strong enough. How will they find it, how strong enough it is? You think they are going to take a section of, build another swimming pool, put it on a weighing machine to find its weight? Then you have to know. You're getting my point, right? You want an 18-wheeler to go on a road, you better have the road be strong enough reinforcement to take an 18-wheeler on there. The 18-wheeler, on the 18-wheeler road, you cannot land a Airbus 320, correct? If you want the Airbus 320 to land somewhere, you need to make your runway with enough reinforcement. So you have to know a priori what are you going to throw on your system. So when an engineer is building this swimming pool, how are they going to know how much mass should be there in the swimming pool? We cannot take a swimming pool and put it on a weighing machine. This is concept number 1 for you. In fluids, we have to think about mass, but we need to write the mass differently. Why can we do that? Because all fluids have a unique property called density. Water has a well-known density. It will vary a little bit based on the impurities, whether it is salt water or it is distilled water, but it is going to be roughly the same. Blood, a fluid, has a well-known density. Oil has a well-known density. Air has a well-known density. So in all fluids have a unique property called density that is inherent to the type of the fluid that has been built. Now since we know the density, we use the concept of density is denoted with a symbol called rho, and we simply write Density, what is density? How is density measured? Mass over volume. So you say density is mass over volume m over v, and this means we can always write fluid masses as density times a volume. You know the density of the fluid, you know the volume of the swimming pool, you make measurements to get volume. That's easy to do. Straightforward. Multiply. That is how you know the mass of the swimming pool. That is how you know how much water you expect to put in that swimming pool, and then make reinforcements so that the swimming pool can hold that much weight. So what we do in fluids is take some concepts from 5A and rewrite them in a way that is more applicable in the context of fluids, that is more practically useful, because mass of a fluid is not practically useful. Mass of a fluid must always be converted into rho times the volume. So for example, we write kinetic energy. What is the expression for kinetic energy? What is the expression for kinetic energy? Half mv square, correct? What should we do to that m? Rho times v. So kinetic energy, when a fluid is flowing, the kinetic energy will become half rho times v, big V, v square. This will cause confusion, correct? You're seeing that. So what you should do is write volume with uppercase. Otherwise, you will ruin your algebra horribly. You're going to get half rho v cube, and you will not know what you're doing. I will write velocity with little v, volume uppercase V. Volume uppercase V, velocity lowercase v, which means we can write kinetic energy as half m v square, which is going to become half rho capital V v square. If need be, put it in a parenthesis so that there is no scope for confusion. This is concept number 1. Concept number 2, force. Force in a fluid. Let's think about force in a fluid. Push a fluid. If you push this table, okay, the entire table moves like this. If I have, say, this much water out here, I poke this water like this, will this entire water move like in the same shape? It won't. So we have to write force in a different manner. What is relevant, what is similar, but not the same. Remember, I am not saying mass is density. I am saying mass needs to be written in terms of density. Mass is not density. Similarly, instead of force, we use pressure. But pressure is not force. I will define what is pressure. But you will see that in physics, in fluids, we will start rewriting this force in the language of pressure, in terms of pressure. Once again, pressure is a very different quantity than force. It depends on force, much like mass depends on density. But much like mass is not density, pressure is not force. It depends on force. So we will write down the next concept that we need. These are two big concepts in fluids that go through a transformation from 5A concepts. One is writing mass in terms of density, and the other is writing force in terms of pressure. So the concept here is that of pressure for heaven's sake or for your sake, write pressure with lowercase p, never with uppercase p. There is power coming up, which is uppercase P. Pressure is defined like this, and I will first write this. Oops. First write this, then I will explain. Area. Is area scalar or area vector? Is area scalar or area vector? How many for scalar? How many for vector? Good. You see this area? How much of it are you able to see now? Same? Is it the same? Is direction mattering? Is area scalar or area vector? Loud. Vector. Area is a vector quantity. I am giving you a demo right here. When is a quantity a vector? When the description of the quantity is incomplete unless we give both a magnitude and a direction. Description of area is not incomplete unless you are told how you are looking at it. What is the amount you are looking at the area? Area is a vector quantity and the direction of area is perpendicular to the surface. So right now this area vector is pointing that way or this way. Generally out of the surface toward you. So if I tilt this area like paper like this, the direction of the area vector is like that. I hold this paper like this, the direction of the area vector is like this. Sounds good? So area vector is perpendicular to the surface. So what is this telling us? This is telling us to consider the component of force parallel to the area vector. This will not show up in the recording. So I will write with this color. Component of force parallel, and I use this sign for parallel, two lines like this. Component of force parallel to the area vector, which is that, and then you divide this by the area. And this tells us whenever we encounter forces in fluids, we have to ask what is the direction of this force. Take a component of force parallel to the area vector at that point on the fluid, use the concept of pressure and rewrite force as pressure times the area. So essentially pressure is the component of force parallel to the area vector divided by the area. Yes.
How is it parallel, perpendicular?
Very good question. It is perpendicular to the surface, but parallel to the area vector. Is that making sense? The area vector is perpendicular to the surface. So the force is perpendicular to the surface. So you can write F perpendicular to surface, or better write parallel to the area vector. It is parallel to the area vector at the local point and then divide by the area. Yes. Same symbol, yes, but momentum is a vector, and we will see pressure is a scalar. Pressure is not a vector. So essentially area is a vector, so we take the magnitude of the force and then magnitude of the area vector, and then we write the pressure. We define pressure that way. Now we are almost getting toward the end of class. So I want to make two closing points in here. Number one, this is where we will continue on to next class, and potentially, time permitting, I will post a recording of one of my earlier lectures to continue this discussion a bit. If you see it, review it before you come for class. Now, one last point, very important point. Those of you who are on the wait list, you should come up to me now after class and fill up this sheet in here. Extremely important, otherwise I can't get you into the class. The class is completely packed. Likewise, if there is anyone trying to switch sections, you should come up here now and let me know what section are you trying to switch to. I cannot promise, but I can try. But this must happen now. I will announce it.
I was wondering if I could schedule a meeting with you regarding physics 5A for grade.
5A?
Yeah, for
Yes, you can. All right. You guys are on the wait list? No. Those of you who are on the wait list and wanting to get into the class, say come to the left. The rest of you who are not on the wait list, come to the right. Wait list questions over here. Now, when you come up here, if you are not in a section yet, if you are in a section, you don't need to, you can go. If you are not in a section, you should write your name, and then I marked out this section numbers and times. Make yourself available for as many sections as you can. If it is only one or two, I cannot guarantee a place in the class. Okay? So just come up here and fill up this page in here. In the meantime, let me take the other questions. Yes.
I needed to change my section to the one on Friday.
Okay, just wait. Just wait here at the end of this line and then come see me.
I was in 5A and now I'm in 5B, but I got administratively dropped because it didn't tell me exactly, but I'm pretty sure it's because I have an incomplete in math due
Okay,
to
just
a-
wait.
Okay.
Just wait. Yes.
Yes, my question is, I don't understand why area can be a vector, in that I don't understand how you know which way the area vector points. Because the area is like a rectangle. How
Yes.
do I know which way it's vector?
It's either in or out, and that is
okay.
figured out in context. So this is a very good question, by the way. So let's say this thing, okay? So I want to know what is the direction of the area vector here. I would say it is either in or out, okay? Now, if I say it is out here, then for this surface it is also that, which means it is in here.
Okay, going into the area itself.
Yes.
Okay.
So in here, out there. So I can choose to say this way or that way. That's my choice. Likewise, if I say it is this way here, I must take it that way there.
And the
So here
direction-
it would be in, there it would be out.
And is that something you choose, or is that something that actually has to do with the area?
No, you can choose.
Oh, okay.
There is one convention, but we'll deal with that later. That is, if it is rotating, we tend to put this counterclockwise rotation as pointing out of the plane, and clockwise as pointing into the plane.
Okay.
But that is only if there is a rotation. You are not going to see rotating fluids.
So
It's going to be static.
all right, and making it a vector is just that we can do math with it. It doesn't really have to do anything about the property of the area itself or anything.
No, it does have to, because for example, let us say here is a surface. Okay?
Yes.
And I apply a push like this. How much is the pressure? Greater than 0, less than 0, 0.
That's greater.
Greater than 0. Greater than 0. Why is that not correct? There is a surface. I push on the surface like this. How much is the pressure? Greater than 0, less than 0, 0. Yes, I push on it this way. Why is it 0?